Hello, this is our project on machine learning. Our topic is on TMDB box-office predictions of the revenue. I'm Mo.
Mine is Isabel.
Since our prediction is done on the dataset given by the website, so we have to understand the dataset itself. So Isabel is going to talk about the description of the dataset.
So here is the given data set, and then as you can see, it's pretty messy. Some of them is in integer, and then some of them is in string, and then some of them is in a list of dictionary. And then here is the visualization of our missing data. As you can see, there are some of them that's missing quite a lot, like the belongs to collection or the budget. And we are going to talk about how are we going to deal with these. So here comes the pre-processing of the data. And then we have some of them like some of the challenges, like some of the items do not have the ID in integer but in string. Like for example, the original language here or even the spoken language here, even after we have extracted the ID of these dictionary is still in string, like the en here or the ar here. So for these kind of data, we are going to do the one-hot encoding for them. And then besides, we have the list of dictionary for some keywords or cast or queries too large, which means like for here, keywords, you see it has a very large list of dictionary, and then for the cast too. So for these kind of data, as we know that not many of them is actually related to the revenue. So we have decided to like for each cast, we'll just like Scott Grimm's. We are just going to get a list of movie that Scott Grimm's have joined, and then also a list of revenue for each of the movie there. So for that list of revenue, we can calculate the variance of the list, and then we can know that how much does Scott Grimm's is related to the revenue. So we will only take those casts that's with the lowest variance with revenues into account. And then the range of value of different column is different. Like for example, revenue, it may has its value ranging from a few million to a few billion, while the runtime is just ranging from like a few thousand. So we are going to do normalization on each of the features. And then the next thing is, even though each item can be represented by ID, there is no correlation between the ID. For example, if my ID is 1 and Mong's ID is 2, then it doesn't mean that we are actually closely related to each other. So we have to represent each of the casts by their mean of revenue. So making the number really related to each other. And then there are also some missing data, so we are going to do imputation, which will be further explained later. And then some of the column have a lots of missing data, which would make a lots of error for the imputation. So we are just going to do experiment on how does the missing rate affect the imputation for all of the imputation method, and then we are going to find out the acceptable missing rate, and then arrange the number of missing data that we want so as to fit the missing rates.
So as continue for the processing, like some of the columns are actually missing data, and you're going to take a lot of time to actually clean and predict the whole process. So in order to compensate with the time of it, we actually have some checkpoints and we save the data in different stages. So we are running like the stages at later stage, so we can actually always refer back using those checkpoints. On the other side, because we are doing normalizing and denormalizing, there are some rounding errors due to the limitations of the type of the languages itself. So we just assume all the budgets that if it's negative, then we just make it back all to zeros because there shouldn't be any negative budgets. And also, nonetheless, is also the number of data of features that actually is too large that for us to actually interpret. For example, like Isabel just said, like we have the ID, but ID actually is not related to the reference itself at all. So actually, we have to do some feature selection process on it. For example, we use the F score and dependency, actually get the dependency higher to the target, which is the revenue itself. Here are some examples on actually we're doing a dependency and F score.
So for my part of the machine learning task, I'm responsible for verification for different predicting methods, like the KNN and the interactive inputer, interactive SVD, the mice, the soft input, and then with different mean, median, most frequent, and constant methods to do the imputation. And then after this, I will have to choose the best method for the imputation, and then also find out the acceptable range of missing rates. And then using the method that I've chosen and also the missing rates that I've evaluated, I'll have to really put them on the training data that we have to work on. So the first method that we have used is KNN, which is K nearest neighbor. And then for this imputation, it weighs the sample using the mean square difference on the feature, which it can find out the K most similar row to our missing row and then do the prediction there. The next one that we have is iterative SVD, which obtain a set of mutual orthogonal expression pattern that can be linearly combined to approximate the expression of all genes in the data set. And then the next one that we have is soft impute, which is just similar to the iterative SVD that we had before, but then it also utilizes sparse plus log-rank structure associated with SVD, which is a proximal gradient algorithm to compute the SVD. And then next we have the iterative imputer, which is a strategy for imputing missing value by modeling each of the feature with missing values as a function of other features. And it is similar to mice that we are going to introduce. So mice is just similar to what we have introduced, and then it's just by imputing based on the relation observed in the data with any other features, like how the features correlated with each other. But then mice is different from iterative imputation in terms of like is filling the missing value with multiple times. So creating a multiple complete data set. And we are also doing the imputation with something like mean and getting the mean and median of that row or the most frequent element of that row, and also filling just with constant value 0. So to do evaluation on different imputation method, we first clean the data and make the data containing only some numerical value. Then we extract the rows that have no missing value, so resulting in like just 1,000 row from the original 3,000 row, and then we save it into a data set like df complete. And then with the df complete, we sample out some of the cells there, making them empty to create a df complete sampled. Yeah, so and then we try to do prediction on this kind of set on the df complete sample, and then compare the result of the predicted df complete sampled with df complete. And we have two ways of evaluating if the result is good. One of them is doing the root mean squared error, and then we do root mean squared error basically for some columns with numerical values or short integers. on a short list. Because for some short lists, we have the production companies, the list is very short. So most likely, if our predicted value is right, then we can really get the ID there. And then we also have hit rates for those with a long list, like for example, keywords and cast or crew. Because, like I said, we have only sampled 3 most significant casts from these kind of lists. So it will be very unlikely that we will get the most significant cast just by doing those predictions. So out of the predicted value, we try to find out if our predicted value is value matching with that long list. So here is the RMSE result for our imputation, and then as we can see that some of them is slightly better than the others. Like for the soft impute is slightly better than like KNN here, or the constant median, or the most frequent value here. And then the iterative SVD is unexpectedly going weird, because I've seen some review on the SVD one, and then it was said that it was not being suggested to use for imputation. And then for the hit rate, we can see that iterative imputer is most likely better for a low missing rate, while the soft impute is better for higher missing rate. So because our missing rate is a bit high because of the limitation of dataset, we have chosen soft impute to be our predicting method for our training and testing dataset later on for the prediction. Besides, we have also tried to combine the dataset, like putting both of the testing set and training set together, and then see if the imputation for some empty cell would be better. But then as compared to the previous result, it doesn't seem that there is much change on it. So as a conclusion, we don't think combining the dataset will improve the imputation.
So moving on to the prediction on revenue, we actually choose 3 approach, including a neural network, decision tree, and linear regression. For each of the model, we also do the denormalized value, which is the actual real value we call it later on, and the normalized value. For example, in neural network, how we do the denormalized value, the real value, is that we first locate our desired features using the dependency we said earlier, and then we have the chosen features to be a feature matrix, and then we use grid search to search for the best hyperparameter we can have, and then we do testing upon it, and then we retrieve our predictions. On the other hand, for the normalized value, we put everything together first. We normalize it with the uniform scale, and then we do prediction using the normalized value, which will have a range have a narrow range for the better predictions. And then after the prediction, we'll put everything back using the same scalar. We invert it back to a real value that we can actually make the predictions actually is in real dollar form. So this is how we do the neural network. And then for the decision tree and linear regression, basically we use the same approach. We have to real value and then normalize the value just to compare the performance and the efficiencies. So here's a result. As you can see, actually, like when we perform neural network, limited by the computation power and the feature we actually have, the loss and the error actually is higher than what we expected. However, because neural network actually right now, like among the 3 of the model we are using, is one of the best, because decision tree actually is a very simple model, and for linear regression, basically just straight line. So right here we have the linear regression model as a baseline model, and then we'll compare the performance and the efficiency based on it, and then we'll just see whether the normalized or denormalized performing better. As we can see here, normalized value actually perform better on both on the test set and the train set. So that's why we